Hello and welcome to this video. Today we're going to talk about finding roots, including bisection, fixed point theory, and Newton's method. So we'll start with the bisection method, which you already know from childhood. In childhood, you must have at some point played this game where you say, I'm thinking of a number between 1 and 100. And of course, if you want to finish the game quickly, you say 50. And then if the person says, nope, it's above 50, you say 75, and so on and so forth. So it's also known as the binary search method, and your goal is to bracket a zero between guesses and to keep splitting your domain. So in some cases, you will have like just a single root. Sometimes you have weird situations where you actually have more than one root in your interval, and you may or may not ever be able to detect it with the bisection method. If you have a duplicate root in your domain, it will not be picked up by bisection. But bisection can be very powerful when your function is otherwise poorly behaved for some other reason. So let's say, for example, this is A and this is B on the axis. Then this guy is going to be B, f of B, and this is going to be A, f of A. Okay, just for example, in this case f of A is negative and f of B is positive. Okay, and the root that we're looking for, let's just label this C, just for the sake of argument. What we're going to do is we're going to split the domain in half, and it's going to look something like, let's say this. M is going to be A plus B over 2 to find the average of A and B. We're then going to evaluate the function, and we're going to get this point M comma f of M, which is either going to replace A or it's going to replace B. So one of the two endpoints will stay fixed and the other one will be taken over. So in this particular diagram, what's going to happen is your A is going to essentially slide, and this is going to become the new A. Okay, so I'm going to trace out what, and we're going to just obviously repeat this over and over again. I'm going to show you the decision tree that most students use when they first attempt to do this, and then I'm going to show you how to simplify that. Okay, so the decision tree, the complex version of the decision tree, and it's okay to do the complicated thing first because you're actually trying to think through this and understand why it works. F of A is negative, f of B is positive, so you have an increasing function. Or you have f of A is positive, f of B is negative, and so you have a decreasing function. Okay? You have one of those two scenarios. Now, in both cases, if you end up with f of m equals 0, we're going to stop. Okay, so we're going to do that in both cases. Everybody can understand that because we accidentally just found the root. This is very, very unlikely. I'm just saying this so that you know if you do happen to do it, you can code this up. If you forget to put this in your code, it won't even matter because this is very rarely going to happen. Okay, but mathematically it's possible, and if you're dealing with polynomials with integer roots and you have an integer domain, then there's a good chance you are going to hit it. So you may as well put it in your code. Okay. Now, you have a situation that f of m is positive. Well, what does that mean? That means you're on your increasing function, and you already hit the positive. That means you crossed the root already. So m becomes the new, I'm just going to use this arrow, m becomes new A, because it means it has to become the new left-hand point because you already crossed over, right? So let's just draw a picture of this to make sure this makes sense. So, and maybe I'm wrong. Okay, so f of A is negative and f of B is positive, so you have an increasing function, and there's 0 somewhere. and we're saying f of m is positive, so m ends up over here. So m becomes, aha, actually the new b. So we double check that and say actually m becomes the new b. Okay, so that must mean if f of m is negative, that means f of m lands like over here instead. If f of m lands over here instead, then that m has to become the new a. Okay, so you just trace out all these cases. Try not to get yourself confused like I just did. F of m is equal to, f of m is negative, m becomes the new a. Okay, and then you're going to keep b, and obviously in this case you're going to keep a. Over here we have a situation m becomes new a, keep b. Let's make sure that that one makes sense. Okay, and if you have a decreasing function, okay, you got f of a is positive, f of b is going to be negative, and then in this case I didn't say what it was. Somehow I managed to not type this in for you. F of m is positive, then m becomes new a, and we keep the b. So what does that look like? So that means you are decreasing, but you have not yet gotten to 0 by the time we reach m, and so you're going to just slide that a over to the left. And then the last case is f of m is negative, m becomes new b, and keep a. Let's make sure that that case makes sense. Okay, so let's just erase this and start over. We have still a decreasing function. A is positive, b is negative. We have our 0 somewhere in here. F of m is going to be negative, which means we did cross over within a to m, so keep the a, and m becomes the new b. Okay, and that's actually more complicated than it has to be, and we're going to simplify it now. So first of all, keep in mind that these two are obviously the same case. If you manage to hit the root by accident, you can just stop and you don't even care which way a and b are. But the situation where your m becomes your new a and you keep the b, that's this situation. So what is the same about these two situations? So let's look and first of all see what's the same about our original two situations. And that would be that f of a times f of b is under 0, because you have a positive and a negative multiplied together, right? So what similar condition do we have here when we want to keep the b and m becomes a new a? Well, the situation is that m is now playing the role of a. So if this condition is true, then this guy, so if m is becoming the new a, then this is going to be true. And so actually I want to make this green so it's more obvious what's going on here. There we go. All right, and I want one more color. Maybe I'll just go ahead and make it gray. This situation over here, what has to be the same? Well, m is playing the role of b, so you must be multiplying by a, and that is smaller than 0. Because if m is being the b, then it's the thing that f of m times f of a must be less than 0. But maybe you don't want to test two conditions. Well, you're going to have to test two things anyway. So figure out how to do that. So what am I going to do for my test? I'm going to do something like this. I'm going to say, okay, simplified decision tree. Simplified decision. You're going to test f of a plus b over 2 times f of b. And then what's going to happen is you're going to end up with 3 cases. You're going to end up with either 0, in which case you hit the root. That's easy enough. Positive or negative. That whole thing's going to be positive or negative. So if this thing is positive, b is going to be a plus b over 2. So in other words, you never really have to calculate what m is. You can just use it. And so in Python, when you say b equals a plus b over 2, it means old b on the left, new b on the left, old b on the right. It's obviously that way because you're in a computer. So if I just write b is equal to a plus b over 2, that's not a math statement, that's a computer statement. Okay? And then over here, I would say a equals a plus b over 2 because m is becoming the new a in that case. Okay? So in your actual code, you also want to keep track of max iterations so you don't get infinite loop. It's not as big of a problem with bisection algorithm, but it could happen, and of course you can just hit Control-C or something to stop it. But it's not a big risk with the bisection method, but we really should get in the habit of always including this kind of thing in your code. So you're going to want to make your function like def binary or binomial. You're going to put in an f, an a, a b, max iterations, and you're going to have some code here, and you're going to want to return an answer. Okay, so you're going to need to do that in the homework, and I'm going to encourage you that you want to actually do the homework properly. I know the internet exists, I'm not stupid, but you have to actually do your own homework, or else what's going to happen is you won't actually get the benefit of being in the class. The purpose of the class is not to find code snippets online and use them to get the homework answers right, because you're trying to build maturity as a programmer and mathematical maturity, and we also are going to do projects. So you could probably get through every single one of these homeworks by finding code off the internet, and that defeats the purpose. But you want to learn how to do this yourself, and that is going to give you the sophistication and the experience and the maturity to get through the project smoothly. If you say, you know, I'm just going to do it this one time, I'm really busy, and you get into the habit of going to the internet too much for advice, what could happen is as the complexity of the projects increases over the semester, you could find yourself struggling more and more, having convinced yourself previously that everything was fine. So my recommendation is to do the homework as intended without too much reliance on the internet. Judicious reliance on the internet once in a while is totally fine, but I want you to mostly try to do these things without getting online snippets of code or advice or chat rooms or things like that. The goal is to try to do it yourself. So having given you the disclaimer, I'm also going to now talk about the last thing I want to say about the binary method is that since every iteration, why does it not want to give me another page? Whatever. Okay. Every iteration you go through divides the domain in half. So if you're going from, you know, A to B, and you know this is 100 units, and you want accuracy to 0.001, how many iterations is it going to take? Well, after the first iteration, you're down to 50, and then after the next iteration, you're down to 25. So you're going to solve some kind of problem, some kind of 2 to the n problem is approximately equal to 0.01, and you're going to solve for n. So you're going to figure out how to do that, and then you should figure out what n is. That's how you do this in theory. And the other thing you can do is when you're writing your code, you could count. So when I count inside to get my max iterations, so I don't want to overrun my max iterations, and so I just return, when I return the answer, I also return the value of that loop that tells me how far I got in my loop. So you can do that, and then it will help you answer these questions like how many iterations did it take for you to do such and such. So those questions can be answered theoretically or by using the computer. My recommendation is to do both. When your code stops, and these are just small little toy problems, you should double check and make sure that this formula agrees. So like, let's say original domain length divided by 2 to the n should be approximately equal to your tolerance. So double check that that makes sense. Okay. Okay, and that's all I need to talk about the binomial bisection method. Not binomial. Why am I thinking binomial? Bisection method, or binary or bisection. Okay. Now, fixed point theory. This is what we're doing next. Here we go. We are going to look for what's called a fixed point. So if you have a function like this, and you have a line y equals x, fixed point is where the function crosses the line y equals x. So this is your function, this is y equals x, and this is your function f of x. So if f of x, well, I lied to you because I only lied that it's being called a g, not an f. Okay. All right. So that's what the fixed point is. We reserve the letter f for the function that has a 0 there. So what we're going to do is we're going to have some function f of x is equal to 0 where g of x equals x. So I don't know. I don't really know what this function looks like. Okay, so some other function. It goes through 0 at the same point where g of x equals x. Okay? So that's the language around how we're gonna talk about this thing. All right. So let's put this down here. Let f of x have a 0 that we wish to find, and create some g functions. I'm going to create 2 of them at the same time, just to save time. g1 of x is going to be x plus f of x, and g2 of x is going to be x minus f of x. In both cases, notice that if f of x is 0, then the g's equal the x's. Okay? And so generically, we will solve g of x equals x where f of x equals 0. So why would we do that? You would think, when I first saw this, I was like, what is the point of that? Because you just took a problem and you changed it, and I agreed that they're equal, but how did you make it easier? That seems like you made it harder, because all the way through algebra, we wanted to set things equal to 0 so we could solve. Now you're saying set it equal to x so you can solve? Yes, because we're on a computer. And one thing that computers are good at is looping. And when you set something up so that the old output becomes a new input, it makes it very easy to code and very efficient to figure out how long it's taking the computer to do something. You know, you're essentially wrapping 2 steps into one for the computer, and it makes the analysis easier. Okay, so example. What are the fixed points of f of g? All right, and I want to write this function. G of x equals x squared minus 2. Okay? And to get the answer, what we're going to do, I'm just going to put it on this side of the screen. Okay, if I have x squared minus 2 equals x, so instead of saying something equals 0 and solving for x, we're going to just say something equals x. But as you know, we're still in the world of algebra. So I'm going to go ahead and set this equal to 0 so that I can actually solve. So right away you're like, okay, you're just totally lying to me. This is not making it easier. But that's because we're just doing the by hand exercise. Okay, x is equal to 2 or -1. Great. So we found where the fixed points are, but the question is, will this work numerically? Will we be able to write code? Okay, will this work in theory, in like, you know, basic theory, like is this even a fixed point, and will it actually work? So first we're going to try to find out if what we did was even right. We're going to chuck these guys back in and see. I'm going to chuck these guys back in here and see if we actually have g of x equals x. So let's just do that real quick. Okay, g of 2 is 4 minus 2, which is 2, so that worked. G of -1 is 1 minus 2, which is -1, so that worked. So yes, that actually worked. Yes, it did work in theory. And will it work actually? Who knows? That's the point of the next part of the discussion. Okay, and it involves actually some computer. Woohoo! So I'm going to go to my Python here. And if you have not encountered this before, you know, I think I can enlarge my font. Hold on a second. Okay, so I'm in Python. Hopefully you can see what I'm doing now. If you have not used lambda functions before, I recommend that you make friends with them immediately, if not sooner, because they're going to make your life a lot easier in this class. So here's the thing. You would love to type the following. You can't. G equals x squared minus 2. Wait, wouldn't you love to be able to type that? But you know that's going to give you garbage. However, you can do the following. Just stick a lambda x in there. That just means we're creating a function and x is the input and x squared minus 2 is the output. Right? Very easy. Then you can use your function notation like you're used to using, and you can say, aha, g of 2 is -2. What about g of 2 is 2? Aha, g of -1. So we just verified that our fixed points were what we said they were. Okay, so what if we're really close to that? G of 2.1. Is that going to be a problem? Yes, that's going to be a problem. Notice that if I go slightly above or slightly below 2, it actually pulls me away from my answer. So this idea that we can somehow iterate towards a solution needs some tweaking. And so what about at the -1? Let's see. It looks like if I'm below -1, it pulls me. It doesn't pull me towards -1. It seems to go farther away. Let me just try -0.9 and see what happens. Yikes. So I was hoping that it would start pulling me in, but it's actually pushing me away. So why is this happening? Let me see. Let me just show you how bad this can get. Let's say x equals -2. We're basically in range 1000, x equals g of x, blah. Okay, now what's x? Well, I just proved that I was not making any sense. Okay, let me try this again. There we go. Why is it taking so long? All right, the computer does not like me today. This is not what's supposed to happen. I'm going to pause this for a second. Okay, let's try this again. I'm just not going to do 1,000 of them. Okay, g is equal to lambda x squared minus 2. But I'm just going to start at x equals 3, and I'm going to say for I in range something really small like 10, x equals g of x. And see, this is what the problem was. I told you that there's no max int in Python. So if this had been on a non-Python system, it would have crashed. But because it's Python, Python's like, no, 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 I can handle this. I can handle this. Don't worry about it. And this is what happened. After only 7 iterations, look how bad it got. Okay, so it actually was doing what it was supposed to do, but it was doing it better than I thought it was doing it. So, I mean, it was worse than I thought it was. So, there you go. So it didn't actually work. So we're going to fix it so that it does work. Okay, so what we would need to do is try to understand what's going on. Okay, and I'm going to draw what's called a cobweb diagram so I can give you an explanation of what's going on. So if you do want to look up something on the web, cobweb diagrams, fixed point theory, something like that, that is something useful to look around on the web for, because they have some really cool stuff out there. But if you have a function, let's say, here's your function, and you want to hit the line y equals x, okay, and you're starting off somewhere. Let's say you're starting off here at f of a. What I'd like to see happen is the following. I would like to calculate a f of a, and what does f of a mean? Well, if you look over here, it means the height on the y-axis. But then your next iteration is going to be on the x-axis, but it's going to be the height you had on the y-axis. So you're going to come over here. Okay, so see what just happened? We went from this point to actually this point. We're moving inwards towards our root. And it doesn't look very cobwebby, I understand, but some pictures look more cobwebby than others. But in this case, we have what's called a contraction mapping. And in this case, we are going to converge. But what we had in the previous situation is we had one of these. It's like we had, this is B, so this is the point B, f of B, right? And if you want to know, like, where is that on the y-axis, you just look at where that is on the y-axis, and then that's the distance at which you're going to end up starting the next iteration. So you really basically just move over to that line rather than going through all these gyrations of, okay, taking this output, putting it down here in the input. And that's why we call it cobweb diagrams, because we leave out all these extra lines and we just say, hey, we're just going to simplify this by going up to the curve and over to the line. And guess what? We converged here, but there's no way we're going to get this guy, because as we're close to this root, it's going to push us away to either of the other roots. And why is that? Well, over here we have another contraction mapping. So in this local vicinity, f of x is a contraction mapping, and in this local vicinity, f of x is not a contraction, it's expanding. I don't know if there's a term expanding map or not, but it's not a contraction map. It's expanding. So it's not going to be an attractor. It will repel this solution, repel us finding the solution. This is an attractor. This attracts us, and this one attracts us. So we can find them. So what was it? First of all, I'm going to give you the cobwebbing rules, because it's just easier to type them out. You're going to start at x naught, then you're going to go up or down, but initially you're going to go up to f of x naught, and then what's going to happen is you're going to repeat. Go right or left to the y equals x line, and then you're going to go up or down to f. And then you're just going to keep repeating this over and over. This part repeats. Okay? So 3 and 4 repeats until you get to your root. So, what we had is we had some kind of function here, and we had in our line, okay, y equals x. If we have something that has a very small slope, then things are going to converge. So let's just look in at the cobweb diagram. What's going to happen if I hit the function here, for example? It's a very, very flat function. I'm going to get cobwebbed into that very, very quickly, right? But if instead I had this kind of situation, the cobweb is going to push me away. So I'm going to try to go up to the function, over to the line, up to the function, over to the line. Even if I'm on the other side, it doesn't matter. It's going to go, here's the function, I'm going to go over to the line, function, line, function, line. So when you have a steep slope on your curve, it's going to push you away from that root. And when it's shallow, what is the magic there? Well, if that derivative of g has an absolute value that's less than 1, we're going to converge, because then we have that magic contraction map. Okay, so let's write that out again. Let's write that out in a way that makes sense. When G is a contraction map, we zoom in on g of x equals x. Yay! So we need the absolute value of g prime of x to be less than 1. Okay? So let's sort of look at this function we've been playing with here and notice something. G is x squared minus 2, so what is actually the function's derivative? It's just 2x. So notice we had two different points. So what is g prime at -1 was one of our fixed points, and another fixed point was 2. So the g prime is just double of the function, and it's actually bad everywhere. Okay, so this is going to be a trouble for us. So let's try to do this problem again, but what we're going to do is we're going to find a way to hack it. We're going to find a way to fix g so that it works, so that it works in both cases. Our hack is going to be, well, hackish after all, but we're going to end up with two different g's. We're going to have a g for each of these guys initially, because we're building up the theory here. Rest assured, this is not how you're going to do things the whole semester, but we have to really understand where this fixed point theory comes from and why we get to the methods we get to. Okay? So let's say if we want g of x to equal to x plus or minus f of x, and we already know g of x, we already have x squared minus 2. So let's go ahead and solve for what f has to be. Right, so we have to reverse engineer f, and so x squared minus 2 is equal to x plus f of x. So x squared minus x minus 2 is going to equal to f. Okay, now what we're going to do is we're going to swap out f for another f that has a fixed point. And generically, we can do the following. I'm going to make my new g. I'm going to call it g naught because I'm going to g2 because we already had a g. So I'm going to call this g2, and then this one g is just g1. Okay, so g2 is going to be x plus, I'm going to put my f of x here, x squared minus x minus 2, and I'm just going to divide by 10. That may be overkill, it may not be enough. We might have to adjust what we divide by, but you have to agree, and I'll show you why. You have to agree that they're going to, if this f shares zeros with this thing here, then the g has fixed points, g1 and g2 both have fixed points at the same x values. So we're doing this as a way of trying to shrink down the derivative on g so that we can hopefully get some kind of fixed point iteration. Okay, so warning, I'm going to warn you when this works, anyway, warning. If you're like me, you're thinking, well, why don't I just crank this up? Why don't I just make this like 1,000 or 10,000? Okay, as you increase this thing that you're dividing f by, we slow down the process. So if you divide by something that's too high for what you need, you're just going to be sitting there forever. But we actually have modern computers that are very fast, so you may not notice. But the more you crank that up unnecessarily, honestly, the goal is to just make the derivative as close to 1 as possible without going over. But it's okay. You can make the derivative very, very small, close to, you can push that down. Keep pushing it down. Okay, so let's go ahead and see what happens in Python. Hello, how come my computer's not giving this to me? There we are. Come on, computer, where did you go? I want Python. All right, now I'm going to change g. I'm going to call this g2 and lambda x. Okay, now what's my new function going to be? It's still going to be x plus something. It's going to be x plus quantity x squared minus x minus 2. Don't forget how to do powers in Python, because don't try to use that symbol or you're going to get bit shifting. Okay, so here's my g, and let me just start with some fixed point. X is 7, and then for I in range 100, I'll make it 1,000, I don't care. X is equal to g2 of x, and then, well, it did not work. So let's figure out why. Did you figure out why? If you did not figure out why, I encourage you to pause the video and figure out why, because I'm going to tell you now if I can get the computer to behave. My computer is not listening to me. It's not letting me move my stuff around on my screen. Okay, so what happens if you take the derivative of g2? We are close to 1, but what are we actually? So the derivative of g2, unfortunately, is 1 plus 1/10 of what? 2x minus 1. So we're still over 1. We haven't actually fixed the problem. We are going to still zoom off to infinity. But if I just change this plus into a minus, we should be all set, right? Because let's just try that. Let's try turning that plus into a minus. Now I'm going to call it g3. Okay, so I'm going to make another function, g3, that's the same as g2, but it's just going to have a minus in there. Then we're going to see what happens. Okay, so g2 was over here. Where did it go? There we go. We're just going to turn this into a minus, and we're going to make this called g3. Now we're going to say x equals 7 for I in range 1000. X equals g3 of x. This time it worked. Okay, so all is well with the world. We managed to converge, but we still would like to get the other root, the -1. So let's try x equals -10 and see if what happens when we start when x equals -10. Yeah, it would help if I could type correctly. What? Overflow? What happened? Okay, so the problem is when x is negative, you probably figured this out. If you didn't, then why don't you think about it for a second. When I put the negative in here instead of the plus, but then I'm going to take the derivative, I'm going to get 2x divided by 10, of course. But that x is negative, right? So I'm still it's gonna be minus a negative, so it's positive. So I'm still having trouble, right? I'm still having trouble. I have created G3, which allows me to find 2 as a root in some situations. But let me try this again. Let's try x is equal to, let's see, just -2. For I in range 1,000. X equals G3 of x, still overflow. All right. However, what if we go back to our other function, instead use G2, and in this case we do get the -1. So what happened is when we looked at G2, so G2 allows us to sometimes allows us, depending on our starting value, so sometimes we can find the x equals -1, 0 of f, or fixed point of g, right? But if we want to find the other root, right? So G3 is equal to x minus x squared minus x minus 2 all over 10. This allows us to find, we can find the x equals 2 root. Why is that happening? Right? So when we choose the minus sign here, it means that for certain initial values we're going to be able to converge because we're very, very close to our derivative being 1, which is what we wanted, and we're just a hair under, which is what we wanted, and then we can converge to the x equals 2 root. But as soon as the sign of this guy changes, this is very brittle because now G2 is going to be the one to converge at x1, but G3 converges for x2. But if you start in the wrong x0, it's just going to break anyway. So this is just really confusing, and you shouldn't have to keep switching between which G you're using in order to get the solution to your question, right? So that's a problem, and so that's why we're going to come up with a new method. But we're going to use some insight from here, because what we just found out was that in this case, why do we have to use G2 over here? It's because we needed to keep all of this negatives and positives under control. I want to just rewrite this as G2, I'm going to say minus -10, okay, in the denominator. So we might choose to divide by a positive or negative value. So we can still use this structure, x minus fraction, old function on top. So let me first say like let's see what this structure looks like. We want a g of x is equal to x minus, this is your old function over here, divide by something. What is it you want to divide by? And when we divided by 10, it worked, provided what? We wanted to make sure this computer is just very jumpy. So when we divided by 10, we wanted this negative here when the derivative of this guy was gonna be positive to bring this down from 1. So you know this derivative is 1 because the derivative of x is 1. So you want the derivative of g to be just under 1. Or if you have to, it can be just over -1. But right now we're in the positive world, so it's just easier to think that way. Over here we had a situation because x was negative, we had to make sure that there was something negative to balance this out. Again, we still needed this whole thing to be net negative. We needed this derivative over here to be net negative to essentially bring, or positive rather, to bring this down. We need to make sure that what's going to happen is compatible with what we're trying to do, and we want to make sure the derivative is, the magnitude of that derivative is staying less than 1. So that's what we're trying to do. I have lost my work. I don't know where it went. Somewhere on this sheet. There it is. Okay. So what we're going to do is we're going to ask Taylor what he thinks. Ask Taylor for advice. Okay? Now we're going to show how to inspire us to arrive at Newton's method. There are many classic derivations of this, and this is just one. There's the graphical, there's the Taylor, there's all sorts of. But right now I'm just going to ask Taylor for advice. I have f of x equals f of x naught plus f prime of x naught times x minus x naught plus other terms, which I'm going to ignore for now. Okay? And what I want to consider is just this part right here. I'm going to consider that. And I know that f of p is 0. At least p is where the fixed point is. It's an x value. P is an x value that causes this to happen. So I end up with f of x naught plus, because I'm going to, let me do this a little slower. Okay, I want to put p in there. Where is the p going? P is going to be where x is. It's going to be right here. P. Okay? P is going to go there, and x naught is whatever your starting point is in your fixed point method. Okay? And okay, and so then the next thing we have to consider is f of x is f of p, because this is where we're starting, but f of p is 0, so that piece disappears. Okay, so we're going to put the p in for x, and then the first term is going to drop out. So what you're going to end up with is 0 equals f of x naught plus f prime of x naught times p minus x naught. So again, x naught is your starting value. Start x here. And p is we want to know. We want to know what point causes this to happen. So if Taylor is saying, okay, this method is going to work perfectly for a line, actually, because if all the other terms are 0, that's what's going to happen. Let's just solve for p. So let me just take this and put this on another page where I can work on it. Okay, so we want to solve for p. Let's go ahead and do that. Why don't you pause the video and solve for p? Okay, solve for p, and I'll see you in a second. Okay, hopefully you solve for p. Now let me try that. Okay, so I'm going to put minus f prime of x naught and p minus x naught on the other side of the equation, and I'm going to say that equals to f of x naught, and then I'm going to divide off by minus f prime of x naught. Aha, that's a clue. And then I'm going to add x naught, And then I'm going to say, hold on a second. So that looks exactly like an iterative method. It looks exactly like what we were looking for. We were asking what it is that we should be dividing by, and we know it depends on f naught. We know that we want it to flip signs when the derivative of f is changing. So it looks like this is everything we've been looking for. So we're going to do the following. We're going to create a fixed point method, and we're calling it Newton because that's what it is. So Newton's method says, Newton's method start with an x naught. So that's your starting point. And then x, the next value, n plus 1, is you take your previous value and you add to it f of xn divided by f prime of xn. Okay, so let's see if I can actually get at this to draw a box for you. Newton says, so this is Newton's method. So just a warning about these, you're going to encounter some issues, and I want you to go ahead and work on the homework and encounter the issues and try to explain them. And I'm going to tell you, sometimes you want to plot the function. It will be very useful for you to plot the function, and you can plot the function with a y equals x line if you think that helps you. But go ahead and use various technology, that could be Wolfram, Desmos, Mathematica, whatever, and make plots of these things so you can try to understand why these things fail or why they succeed. Okay? And I will catch you on the next video, or hopefully in class.